full size surrounding dirt. Person who produced something. Person introduced to silver and age. And then to the maps. Return F string this F string row minus W is self and I am self result. Nice. Celebrate birthday, so age. Person one, introduce. Person two, print. Person one, celebrate birthday. Print. Person two, celebrate birthday. Run it.
Even if your team's not in the same place, your work can be. You just need Asana. Asana organizes work, so teams know what to do, why it matters, and how to get it done. Try it for free at asana.com. That's ASANA.
That's a trash river. There's no water, it's only trash. This is insane. They're actually making all the shirts and the clothes here. That's why there's so much trash. Very interesting. On the other side,
What I've fallen in love with. The magic you are looking for is in the work here. Hard luck.
Oh my.
Nina, and I'm here with what?
Bank account unit, self account number, account holder balance, deposits. So sorry, these bank account function in it in the bank account self account number, account holder balance, deposit, F string deposit, dollar amount down. dollar amount, squiggly brackets. All right, here we go. Bank account. Def init. Account number. Account holder and balance. Self account number, self account holder equals account holder, and self balance equals balance, and this one is so if statement. So deposit amount. Let's comprehend this really quick. If amount 0, self balance plus equals amount return F deposit. So deposit, if the amount is more than 0, the self balance plus equals that amount. Return the deposit deposited, the dollar amount, the period, and the new balance is dollar self balance. And string. So balance. If anything else returns as invalid deposit amount. Okay.
Are you a virgin? Yes, yes. That's right. I am, yes. Unfortunately, I'm not married. I'm very great, and I have still two things to marriage. So, why is it that you chose marriage? Especially at the minute, one day. Honestly, it was a decision that I made when I was really young. It's my son, Bryce, it comes out. When I was really young, and I came across this another listen name, maybe I should wish on me, the big name, develop also something else. It was like, well, something young is surely fine. And now that she's got, relationship with somebody else, or going to somebody else, or she's with somebody else, there's going to be some level of with the intimacy. And it's supposed to be just between me and my ex-partner. And then later in life, we started in sex education, like thinking that right then, when I first learned what sex was, it was like, this is it. This is what man and woman who are committed to each other in marriage should do exclusively. But are you also looking for a virgin? No, that's a good question. I gotta be.
Deficiency. Iron deficiency, man. Yo. That one was a good one. One. Let's get this done. Let's get this done. Go through all of these. Got it. This one is bank account. So we'll start with the project and then we'll do transaction history next. Okay, here we go. Deposit and then if the amount is more than zero, the sell balance is going to be plus the amount. Return when deposited dollar amount, new balance. New balance is the self balance dollar amount there. The amount though, that is already, oh, there it is. Okay. Invalid deposit amount. Phone will def withdraw self amount if zero amount self balance If the withdraw would be, it would be the opposite of this, slightly. When we withdraw, if zero is less than whatever the amount is, equals the self balance. So self balance is minus that amount. Return withdraw withdrawn dollar amount, new balance dollar self balance. Else return insufficient funds. Nice. Insufficient funds or invalid withdrawal. Get balance. So which means return f string account balance for account number account holder new balance. So so balance so account holder self account holder number so the string is string defined submitter class is actually the same mechanism as for object instances applies for types. There are just objects themselves. There are there are converted strings by
The Demolisher. Superman invented a new superhero persona to get away with brutalizing his villain.
oh man.
From birds to fish, ants to humans, all of the living organisms that you can see around you exist thanks to evolution by natural selection. Yet these origins lie hidden in an unseen microcosmos.
Now we show this. So this is the program. This is the program. Now we can just make up something like bank account which equals is it it's account one bank account 1 2 3 4 5 Alice $1,000. This what is that what that's saying? Account to bank account two where's there? Ah, Bob. Print account one deposit two deposit 50 do 2 1. So withdraw print account one withdraw 1,000 to 150 print account one two withdraw about $900 and display it. So print print account self number print account one get balance print account one account two get balance. So it's done. Let's go. Nice. Define the type of data. Type is um, class. Template, which can which have the instances. at this functional operation as well. So we're here, template slash blueprint for creating objects. Init function to define the variables that are in it, Um, define function
the cellular world. I've been interested in these processes for a while, but as a computer scientist and not a biologist, I've been exploring evolution through a lens of programming. In this video, I'm going to show you a simulation that I've been working
init
on
function to
and
define
introduce
the
you to some of the
variables that
interesting
are
emerging
in
dynamics of this world.
deposit.
As with any computer simulation of a real-world process, we'll be making vast simplifications of the system we're studying. For me, this has been a great excuse to learn some biochemistry, and I decided that what I was most interested in is the evolutionary bridge from single-celled organisms, called protozoa, to multicellular systems. This was a key transition on the path from the microcosm.
Recently, and for no reason at all, I asked Mint Mobile's legal team if big wireless companies are allowed to raise prices due to inflation.
10,000. After 10,000 generations of evolution, this colony survives better. We're now up to 80% of the population making it to the spawning areas. The last run, only 72% of them made it. These bigger brains let them evolve quicker. They have better mental capacity to allow them to find a solution that works. And if you're a programmer and you're used to neural networks, you know this phenomenon where a neural network solves some problems, but it's hard for us humans to intuit just exactly how it works. If you look at one of these brains, if you took a pencil and paper and a calculator and started with the values of the input sensor neurons, you could figure out all the numbers that go on, and you can figure out exactly why it behaves as it does. But why should we? With many neural networks, when they work, why not just accept it? Let's go to more extremes and run this again with a genome of 1,000 genes, allowing 1,000 neural connections and up to 127 internal neurons. Now, this one took a while to compute on the computer I'm using, but after letting it run all day and getting to generation 10,000, here's what we have. We're up to 93% survivors or reproducers. That's the best yet. Their bigger brains give them a distinct advantage. In this colony, there are many different strains, as you can tell by the different colors. The majority of them have brains that are wired up more or less like this, and this is definitely too complex for a human being to understand how it works. And so here's what we found out. With only 2 brain connections and 1 internal neuron, 60% of them managed to survive the selection criterion and reproduce. With 8 connections and 2 neurons, 72%, 32 connections, 5 neurons, 86%, and with 1,000 connections and 127 internal neurons, 93% survived and reproduced. The takeaway message here, I guess, is that your neurons are valuable. They serve you well. Take care of your neurons. Now, let's move on to talk about the kill neuron. But before we run an experiment where these creatures kill each other, let's first talk just a minute about the encoding scheme we use for the genomes in the simulator. Some of my programming friends are curious about that. If you want to skip right to the next simulation, you can skip forward about 2 minutes. Our simulated genomes consist of genes, where each gene is represented by 8 hexadecimal digits. Let's just take this one gene, for example. This one gene, 8 hexadecimal digits, represents 32 binary bits of data, and each 32-bit gene is divided into 5 different fields. There's one field of a single bit that determines whether the source of the connection is from an input sensory neuron or from an internal neuron, and then there is a 7-bit field, which is an identifier of which input neuron or which internal neuron. We take that 7-bit field as an unsigned value and take it.
Meaning it is adding more of something into the couch. Deposit, deposit. I'm trying to find statements. Amount of myself blocks. Invalid, invalid, um, invalid statement, return statement, it, then else function. Define, define, if, then else. Return statement. It similar to deposit is um, subtracting subtracting B similar to deposit is subtracting an amount to its showing the return function to show the changes from subtracting.
Demonstration distance and range just
Oh, should I keep? Whoa. Get balance function to show the current balance and counter current balance from the user account. User account. Balance string function to show the info about and I define variables for the print lines. Define variables for print lines. Print lines to show print lines with input input information print with info. Define variables for print lines down below. I mean to just define variables for print lines. Print line. Print line with input with input information with variable. Define variables for lines. Lines down below. And then let's see. Down arrow pointing down the Python. Let me think. Or or lines and on. Print account line, deposit print line with variable. Variables account one, account for two, along with the deposit and the option. Let's print variable. Print account one, get balance, print with info. Print print line with variables along with balance function. So, two. And it's coming on. Ooh.
So mark your calendars for Saturday, October 20th, because we have a whole day. February so my mom, you're like, "Mẹ, con bây giờ chẳng rายการประมาณที่คุณชอบไปไม่ติจังแต่ไอ้แกมันแผ่นยังไงนั่นก็อัด
Berlin. Hold on. Americans. And transaction history. Adding transaction history. Adding transaction history for rather development. So I think this is deposit. And import. Transaction date time dot now. Deposit comment.
Comparative monitor, right now, I'm in this with the son. I want to see him that. Hell, it's all just like, come on. What is it?
Can't tell you how beautiful it is to listen to testimonies of Muslims who have come to know who Jesus is.
I don't do that.
How you feeling right now? I'm feeling great. I'm feeling fantastic. I want to thank Riyadh and the Kingdom of Saudi Arabia for giving me this opportunity to prove people wrong one more time again. Might come out short today. I might be wounded, but I'm not advancing yet, man. I got mine, I got mine. I'm still a fighter, and I'm ready to fight anytime. We got running back again. When the fight started, one thing, when we
Nobody knows that I'm a cook.
She looks like a girl. She looks like a girl.
Take a look at these diamonds from this alive for squinting artist. With faith from Victor Finch, you already fixed on heart like that. On October 29th. This is what Travis Kelce did. This is what he did. That's young Joe. This is birthday. This is making birthday, right? This is birthday. This is young Joe.
So deposit.
Your brother Tristan was in my DMs, really sincerely trying to convince me.
Wow, I got a fresh check.
All right, here we go. All right, so right when you get the balance is when the transaction happens. So that's the transaction date time now. Getting the date, getting the time for the transaction history. And then you get the deposit amount. Deposit amount. Here as well. Also the transaction equals date time now. Deposit deposit amount. It's withdraw. It's withdraw. Withdraw. Yeah. Not withdraw. Withdraw. Not. End of statement. Oh, there you go. Transaction. Transaction. Function or method. Method to attach date, time to withdraw hours. Deposit out. One, which one good, same as this one. Get, oh, get the transaction, or just get transaction history. So we'll do return of transaction history. Return some transaction history. Those we also got. And put it on my hand and scroll through. Hit print. Print. Transact. Print. Transaction history. 4 times transaction type. And transactions. Print. Print. Add. Print. Add. Print. Add. Sounds. Transaction history of time stamp. As action type. And the print. Oh. Nice. Try that again. What is running? Come on. Come on. Come on. Come on. Run. Let's go. Come on. What is going on?
Huh? I'm going back to Africa. No, he doesn't like life. No, this is with the life. In Texas, look at that here. How? People in Africa are surviving just the life. How do you mean? Look at the life. Look at how this is not survive, man. I cannot do this.
What's going on here? Why is this not working?
In detail the events that unfold on a macroscopic scale. But when we venture onto smaller scales, it's as if we're entering a parallel reality whose workings escape us. In this world of the infinitely small, the laws of physics and relativity we know no longer apply. Instead, we find strange, sometimes invisible particles interacting in such mysterious ways that we find it hard to believe they actually work. Quantum physics, string theory, supersymmetry, the uncertainty principle. So many expressions that attempt to describe the mechanisms of this invisible reality to make it easier to understand. Unfortunately, some parameters still elude us, and it's possible that mankind's intellectual capacities will never allow us to tame the events at the heart of atoms. That said, as long as the mystery remains, research will continue. Each discovery inevitably raises its own set of questions. By probing the microscopic world, scientists have been able to venture deep into nature's smallest universe. While a few decades ago, we thought that atoms were the inseparable building blocks of matter, today we know that these elements are home to an incredible bestiary of particles. Quarks, gluons, Higgs bosons, neutrinos, photons. It's enough to make you dizzy. To say that these elements are minuscule is an understatement. To understand this, let's compare scales. Observations of the cosmos tell us that the diameter of the observable universe is around 93 billion light-years. Until recently, the number of galaxies in the universe was estimated at between 100 and 200 billion. According to the latest estimates, there are in fact 2,000 billion. In fact, our Milky Way is just a tiny drop in the cosmic ocean. Yet from our perspective, its dimensions are inordinate. It's estimated to be over 100,000 light-years across. That's enough to house between 200 and 400 billion stars, and probably more than 100 billion planets. Among these stars is our Sun, nearly 700,000 kilometers or 430,000 miles in radius. That's around 10 to the 9th power times the diameter of the Earth. Our beautiful blue planet, gigantic to our eyes, is in reality invisible in this cosmos. For if the solar system were a city 20 kilometers across, the Earth would be little more than a grape. And yet more than 8 billion human beings now live on it. But then again, appearances are deceptive, for man is far from occupying all the space available on Earth. If we were to group together all the human beings currently living here, they would fit on an area equivalent to the city of Los Angeles. So, compared to a modestly sized terrestrial planet, man is a grain of sand. If this scale comparison gives you a slight headache, just wait for the next part, because it's possible to go much further. Each human being, however microscopic compared to the cosmos, is made up of around 30,000 billion cells. And these tiny cells, observable only under the microscope, are themselves made up of 100,000 billion atoms. This figure varies greatly from cell to cell, but it's still completely excessive. Wait, we can go even further. If we look at the heart of atoms, we'll be amazed to discover that they're 99.9% empty. In other words, the elementary particles that give life to atoms occupy just 10 to the minus 14 power percent of their structure. We can say it. Matter is theoretically made up of nothingness. It sounds crazy, but hidden in this nothingness are tiny elements of the quantum world that give life to the reality we know. And although we are made of atoms, their profound nature seems even more distant than the confines of the observable universe. So the infinitely small conceals many mysteries. Dear traveler, good morning. Today we're off to explore the heart of matter in the infinitely small. Together, we'll try to unravel its secrets by literally looking deep inside ourselves. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip.
Oh, self.
Before embarking on our journey into the world of the infinitely small, we must first take a look at the world around us. As you know, it is governed by physical laws that seem immutable. These include Albert Einstein's general relativity, Newtonian mechanics, and Maxwell's classical electromagnetism. But to get down to the quantum scale, you'll have to forget a lot of these general truths. In this world, we observe intriguing phenomena that are not taken into account by the classical laws of our reality. Would you like an example? Well, in that case, do you know anyone who is both dead and alive? Apart from in George Romero's zombie films, this is quite impossible. These two states are quite distinct. Nobody can be both dead and alive, at least in the literal sense of the word. But in quantum physics, things are quite different. A particle can exist simultaneously in several different states. This phenomenon is known as quantum superposition. It's perfectly illustrated by the famous Schrödinger cat thought experiment, formulated by the physicist of the same name in 1935. In this experiment, we imagine a hermetically sealed box containing a cat, a vial of poison, a device for detecting radioactive particles, and a piece of radioactive material. When the radioactive material decays, it triggers the detection device, shattering the poison vial and killing the cat. According to quantum physics, before the box is open for measurement, the state of the system, the cat, the radioactive material, and the poison is described by a quantum superposition. This means that the cat is theoretically in a state of superposition, both dead and alive, until the box is opened. Obviously, this funny experiment doesn't reflect reality on a macroscopic scale, but it does help us to understand the phenomenon of superposition specific to subatomic particles. Do you find it strange? Well, we've only just scratched the surface of the oddities lurking in the realm of the infinitely small. Within it, we also find quantum entanglement. This law tells us that when two particles are entangled, their quantum states are inseparably linked, regardless of their spatial distance. And if two particles are in a state of entanglement, only a measurement will tell us which final state they will adopt. A measurement made on one of the two particles will instantly affect the state of its twin particle, even if the two are separated by great distances. It's as if the two entities could communicate immediately. At an instantaneous speed that exceeds the speed of light, challenging the laws of modern physics. We call this a phenomenon of non-locality. All this may seem very complex to you, and so it should. Quantum physics is totally counterintuitive. So much so that more than one physicist has torn his hair out trying to unravel its secrets. But don't worry, we'll be coming back to the specifics of quantum physics in greater detail as we continue our journey. In the meantime, let's get back to the macroscopic world around us. Like Erwin Schrödinger, we too are going to conduct a thought experiment. And to do so, we're going to imagine that we have the ability to grow and shrink at will. A bit like Marvel's superhero Ant-Man. With this power, we can travel close to Mount Everest, the highest mountain formation in the Earth's crust. Its highest point is almost 9,000 meters, or 29,500 feet above sea level. So we're going to grow until we reach that height. Let's just say that this will be our starting point for our descent to microscopic scales. But to shrink, we need different frames of reference. In this case, after the highest natural formation, it makes sense to head for the largest human construction. For that, we need to go to Dubai, to the Burj Khalifa. This gigantic tower is 828 meters or 2,700 feet high. Now, let's go down another level and measure up to the largest animal on Earth, namely the blue whale, a whale that can reach 30 meters or 100 feet in length and weigh close to 200 tons. And this same whale feeds on plankton, a collection of very small organisms that live in aquatic environments. Their size varies considerably according to the type of organism, but the smallest of them measures no more than a few micrometers. That's 1,000 times smaller than a millimeter. Thanks to our superpowers, we can shrink to the size of microplankton to observe them. We're tiny now, but we're still a long way from the atom. Like bacteria and other single-cell organisms, we're the size of a cell, but we've yet to scale up to the size of a virus. Yes, viruses are much smaller than bacteria, although the two are often wrongly associated. Bacteria are micrometers in size, so they're easy to observe under an optical microscope. For viruses, things are very different. Viruses measure between 20 and 300 nanometers. They are therefore between 10 and 100 times smaller than a cell. But make no mistake, this ridiculously small size makes them extremely dangerous. These microscopic entities are composed of genetic material, such as DNA or RNA. They are then said to be intracellular parasites, as they reproduce inside the host cells they infect. Although they are not considered living beings, they can still replicate and propagate autonomously. Anyway, back to our descent into the world of the infinitely small. If we take the size of the smallest viruses, i.e. around 20 nanometers, we're still giants compared to the elementary building blocks that make up matter, the famous atoms. Their size varies according to the element in question. But overall, they are of the order of 10 to the minus 10 power meters, or 100 picometers, or 0.1 nanometer. This is particularly true of the hydrogen atom, composed of just one proton and one electron. It is 2 times smaller than a carbon atom, whose diameter is around 0.2 nanometers. That said, talking about the diameter of an atom is a gross simplification. In reality, its size is determined by the distribution of electrons around the atomic nucleus. Most of an atom's mass is concentrated in its nucleus, which is itself made up of protons and neutrons. Electrons, on the other hand, are much lighter and occupy a much larger volume. So, the size of an atom is determined by the volume the electrons can occupy around the nucleus. This is the electron cloud. The electrons always remain at fixed quantified distances. These are called outer electron layers. All this may seem rather complex to you. To illustrate this distribution, let's take an example with elements on a macroscopic scale. Imagine that the moon is an electron and the Earth is the nucleus of an atom. In this hypothesis, the moon can orbit the Earth, but only on certain well-defined radii. Also, imagine that the moon does not move on a two-dimensional plane, but on the surface of a sphere. Its position takes into account all 3 dimensions of space, but always with a fixed distance from the Earth, corresponding to the various external electronic layers. The moon can potentially be found anywhere on one of these layers, with greater or lesser probabilities of presence in certain places. And the only way to know its exact position is to take a measurement. By repeating the measurements a large number of times, we can then estimate the probability of presence for each zone of each layer. It's exactly the same principle with the electrons that gravitate around atomic nuclei. This uncertainty about their presence is purely quantum in nature. In reality, The Moon does not behave at all like an electron. Its position can be determined with great precision, simply by calculation, and without direct observation. But due to the quantum nature of electrons, their exact position at a given moment is always unknown if no measurements are taken. In physics, this is called an atomic orbital. This is a mathematical function that gives us the probability of an electron's presence around a nucleus in a given region. Keep these explanations in mind, as they will be useful for the rest of our journey. They also help us to understand why atoms, falsely represented as marbles, are in fact mainly made up of vacuum. To better understand this, let's return to our hydrogen atom and shrink it down to its size of 0.1 nanometers. At this point, we're fast approaching the infinitely small. At 0.1 nanometers, we're smaller than mankind is in relation to the Sun. To understand just how disproportionately small atoms are, we can also give the following estimate. The body of an average adult would contain 100,000 times more atoms than there are stars in the entire observable universe. In other words, something like 7 times 10 to the 27th power atoms. When you hear these figures, your brain may be on fire. But to really observe the smallest known elements of matter, we still have to go all the way down to its heart. And once again, the drop is dizzying. As we said, the hydrogen nucleus is made up of a single proton. This proton is not a picometer, but a femtometer. That's 10 to the minus 15th power meters. To be more precise, the size of a proton is 0.877 femtometers. Hydrogen's core is therefore 10,000 times smaller than the atom itself. To give you an image, if hydrogen's atomic cloud were the diameter of a soccer stadium, its nucleus would be no bigger than a marble placed in the center of the pitch. As for the electron, it is considered an elementary particle, i.e., it is not made up of smaller parts. It is very difficult to estimate its size, which has never been precisely determined. However, scientists agree that it would be less than 10 to the minus 22 power meters. So, to return to our soccer stadium example, if the proton is a marble in the middle of the pitch, the electron would be no bigger than the smallest virus. Just as we are unable to imagine the infinite expanse of our universe, we are unable to conceptualize the size of the most elementary particles. In any case, after this formidable descent into the realm of the infinitely small, we can now plunge into the heart of atoms. We are now on the scale of atoms, but before we discover what's hidden deep inside them, let's first take a look at how they behave in relation to each other. As you probably know, all the matter around us is made up of atoms and molecules. We can interact with it, and our bodies are subject to the same laws of physics. Hypothetically, there are also other forms of matter that don't interact with the atoms we know. The most famous of these is dark matter. But to avoid getting lost in the limbo of the material world, we'll concentrate solely on known matter. As we've just explained, everything around us is made up of atoms. Your body, the food you eat, the clothes you wear, the air you breathe, or even the screen on which you're watching this video. But to form the countless types of elements we know, atoms have to come together and combine. This is how molecules are born. For example, a hydrogen atom can bond with another hydrogen atom to form dihydrogen. Two hydrogen atoms can also bond with an oxygen atom to form a dihydrogen monoxide molecule. In other words, a water molecule. It's as if each atom were a Lego brick with its own shape. Bricks can be assembled by certain forces, deconstructed by others, and reassembled to create a new element. This cycle of creation and destruction is happening all the time, all around us. Sometimes it gives rise to small molecules like dihydrogen, dioxygen, or even dinitrogen, each composed of just two atoms. But in other cases, the molecules created are extremely long and complex. These are known as macromolecules. This is particularly true of polymers, long chains of molecules with interesting physical properties. There are natural polymers, such as the starch in cereals or the nucleic acids in DNA. There are also synthetic polymers, the famous plastics such as polystyrene. But one of the largest molecules is a natural protein called chitin or connectin. It's also the largest known protein. It plays a crucial role in muscle structure and elasticity. If you want to name it by its scientific name, you'll need a lot of courage, because its name is made up of over 64,000 letters. As for its size, it can reach several micrometers in length, due to the 30,000 or so amino acids that make it up. All this makes us wonder about the forces that enable such tiny atoms to bind together to form elements as complex as they are strong. Naively enough, we might think of gravity. Unfortunately, its intensity is linked to the mass of the objects. Since atoms have virtually zero mass, this hypothesis is out of the question. But then, how do they relate to each other? Well, to find out, we'll have to go back to our physics and chemistry lessons. Let's start with the best-known bond, the covalent bond. In a covalent bond, atoms share one or more pairs of electrons to achieve a more stable electronic configuration. The shared electrons create a mutual attraction between the atom's nuclei, thus maintaining the bond. To put it more simply, it's as if two atoms pooled their resources, in this case electrons, to guarantee their stability. Let's call it an exchange of courtesies, if you will. The covalent bond is the strongest and most widespread atomic bond. But there are also so-called ionic bonds based on the same principle. Here, atoms transfer all or part of their electrons to form positive and negative ions. An ion is simply an atom that carries a positive or negative charge due to a lack or surplus of electrons gravitating around it. Yes, electrons are particles with a negative electrical charge. As a result, the forces of attraction between ions of opposite charge hold atoms together. Do you still follow? Normally, yes, because so far we haven't tackled very complex subjects. However, when our journey takes us into the realms of quantum phenomena, things are likely to get a little more complicated. But back to our bonds. In addition to ionic and covalent bonds, there are also metallic bonds. In this case, atoms release their electrons in the layer furthest from the nucleus. This is called the valence shell. The electrons thus release spin between the metal atoms, creating an electrostatic attraction between the positively charged ions. The result is the solid, malleable structures typical of metals. Perhaps you're also familiar with van der Waals forces? These are exerted between molecules at short distances, but their impact is rather weak compared to the previous bonds. They are due to temporary fluctuations in the distribution of electric charges, creating an attraction. Finally, there are hydrogen bonds. These come into play when a hydrogen atom bonds to a highly electronegative element. In other words, an element capable of strongly attracting electrons to itself. Examples include oxygen, nitrogen, and fluorine. In this configuration, the hydrogen atom develops a slight positive charge as its electron is partially captured by another atom. This creates an electrostatic bond known as a hydrogen bond. These bonds are stronger than van der Waals forces and are at the root of many biological and chemical phenomena. For example, they enter water to form droplets that adhere to surfaces. It is also this force that enables geckos to climb walls. Hydrogen bonds are even involved in the stability of proteins and the structure of DNA. So without even getting to the heart of atoms, we can see that they are incredibly complex. They obey forces of their own, which give rise to the laws of matter that we observe on our own scale, yet are unable to understand. And now that we've seen how many atoms behave in relation to each other, it's time to continue our journey by observing them in isolation. Just as there are large individuals and smaller ones, atoms come in many different forms. These shapes are characterized by the number of electrons they possess and the elements that make up their nuclei. These elements are called nucleons, but you probably know them better as protons and neutrons. The more nucleons an atomic nucleus possesses, the more massive the atom that carries it. In fact, hydrogen, with just one proton, is the lightest atom. As for the heaviest atom, it's uranium-238. Its nucleus contains 92 protons and 146 neutrons. Despite being the most massive of the atomic bestiary, its mass remains ridiculously low on our scale, around 4 to the 10 to the minus 25 power kilograms. And if you're wondering about its diameter, it's 350 picometers, or 0.35 times 10 to the minus 10 power meters. And yet, it remains the king of all atoms found in nature. Other, even more imposing elements have been created in the laboratory. Not least, oganesson, officially the heaviest element on the periodic table. Artificially synthesized for the first time in 2002, it is highly unstable, disintegrating in less than a millisecond. Today, many scientists believe that it is impossible to create a new, heavier element, but others maintain the opposite. In any case, to avoid making things unnecessarily complex, we'll continue our adventure at the heart of a simple atom, the oxygen atom. The oxygen atom contains
allows
16
you to keep track
nucleons.
of
That's
what
8
has
protons and 8 neutrons. Around this hard core gravitate 8 electrons. These form what is known as the atom's peripheral cloud. Since electrons are negatively charged particles, they are attracted to positively charged protons, a bit like the north and south poles of a magnet attracting each other. In fact, this electrostatic attraction maintains the atom's structural integrity in perfect charge balance. And yes, while atoms bind together via various cohesive forces, other forces are also at work to ensure their stability. Let's do some elementary physics. At present, it is estimated that 4 major forces govern our universe. These are known as the fundamental interactions. On a macroscopic scale, the 2 most prevalent interactions are gravitation and electromagnetism. But at the center of atoms, other forces take over. These are the strong and weak nuclear interactions. The strong interaction holds the atomic nucleus together. This extremely powerful force acts between nucleons. It holds protons together, despite the electrostatic repulsion due to their positive charge. To take the example of magnets again, you've no doubt already tried sticking 2 magnets with the same poles together, which tend to repel each other. Here, we can make the following analogy. The magnets that repel each other are the protons, and your hands that exert pressure to stick them together are the strong nuclear force. Just as gravitation is ensured by gravitational waves, the existence of which was recently demonstrated, the strong nuclear force is ensured by strange particles called gluons. Don't worry, we'll come back to this in the next part of our atomic odyssey. As for the weak nuclear forces, they act between leptons and quarks. In simple terms, leptons are simply elementary subatomic particles like electrons, and quarks are the building blocks of protons and neutrons. Weak nuclear forces are responsible for certain types of radioactive decay, in which one particle is transformed into another. These are mediated by other subatomic elements called bosons. Once again, we'll explain all this in more detail. As we turn our attention to the forces that maintain the internal organization of atoms, we slowly begin to scratch their surface. This microscopic excavation allows us to discover many more of the strange particles mentioned above. Now it's time to continue our exploration and meet the subatomic particles. A formidable bestiary of small mysterious elements, which are nonetheless at the origin of the reality in which we evolve. Let's take a look back at our journey so far. Our observable universe is about 93 billion light-years across. Within this cosmic immensity are galaxies, which cluster together in clusters. Galaxies, usually 100,000 light-years across, contain an incredible quantity of stars, stellar gas, and dust. These stars, millions of kilometers across, usually capture planets in their orbits. And we know for sure that one of them contains life, our beautiful blue planet. Everything we can see with the naked eye, from the tallest skyscrapers to the tiniest fleas, is on the so-called macroscopic scale. Then there's the microscopic world, which can only be seen through a microscope. That is, with dimensions smaller than 0.1 millimeter. But if we go further down, as we have done, we find that living beings are made up of cells. These, in turn, are made up of DNA, itself made up of smaller elements. But what are molecules if not an assembly of atoms? And what are atoms if not a bubble of vacuum, in which electrons, of an elusive nature, move around a nucleus of nucleons, all governed by strong and weak fundamental nuclear interactions? This descent into the world of the infinitely minuscule is already incredibly dizzying. And yet, it's possible to go even further. Yes, even further than if we were to go to the very edge of the observable universe. On such a scale, the journey seems infinite. For at the heart of protons and neutrons, we find yet more elementary particles, the famous quarks. While ancient Greeks such as Democritus and Epicurus had theorized about the notion of atoms in their time, without being able to validate this hypothesis, the word would be revived many years later in the 18th century. Scientific progress had made it possible to prove the existence of these elementary building blocks of matter. Physicist John Dalton was one of the first to revive the concept of the atom in the 1800s. Subsequently, other scientists such as J.J. Thomson, Ernest Rutherford, and Albert Einstein validated and enriched this hypothesis. It would be demonstrated that the atom is not unbreakable or indivisible, as the Greeks thought, but rather that it is a mainly empty body, in the strictest sense of the term, composed of an electrically charged nucleus around which electrons move. Einstein also demonstrated the wave corpuscle duality of particles such as photons, laying the foundations for quantum physics. Yet little did these brilliant minds realize that the atom was not the end, but a new gateway to an even more complex world, the so-called subatomic universe. And its main occupant is none other than the quark, which we mentioned earlier. Let's take a closer look at the quark. It will be an excellent introduction to the subject before we go on to discover more about its congeners. First of all, it's important to remember that a quark is not a single entity. It's a term used to describe a group of fundamental particles. We speak of fundamental particles when they cannot be divided into smaller parts, at least not according to our current knowledge. Quarks are therefore considered the elementary building blocks of matter. They are responsible for the formation of protons, neutrons, and other subatomic particles. The discovery of quarks dates back to the 1960s, when physicists Murray Gell-Mann and George Zweig independently proposed a theory, soberly entitled quark theory. They put forward the hypothesis that protons, neutrons, and similar particles were made up of smaller, indivisible particles. It wasn't until 1975 that the first quark was observed experimentally, thanks to CERN's particle gas pedal. This technological feat is located on the French-Swiss border near Geneva, and is also known as the Large Hadron Collider, or LHC. A circular tube, 27 kilometers or 18 miles long, buried underground, it accelerates particles to near light speeds until they collide. The result is a microscopic shock, but one of unprecedented violence, enabling matter to be fragmented to reveal its constituent parts. But let's get back to our little quarks. We currently know 6 types, the last of which was discovered in 1997. Here's the list. 1. Up quarks. 2. Down quarks. 3. Strange quarks. 4. Charm quarks. 5. Top quarks. 6. And bottom quarks. Each of these quarks has unique properties. These include mass, electric charge, and spin. Their charge is said to be fractional, corresponding to either 2/3 or -1/3 of the charge of an electron. As for spin, it's important to define this notion, as it's ubiquitous in particle physics. It's a quantum property that indicates how a particle